Hello everybody, and welcome back to another lecture video. In this lecture video, we're going to be talking about vector addition using the parallelogram method. So kind of the idea that I have it in brackets, parallelogram method, will lead you to believe that there is more than one method, and as you guys will see, there are more than one method to add vectors together, but we're going to start off with the parallelogram method. This is the more theoretical method, as you will. And it sucks ass. I'm going to be honest with you guys, full transparency, you guys will not like this method. The second method that we cover in the next video, it's much more preferred, much more simple, but of course it's in the program, so we have to learn it. Now, I want to touch on something real quick. As I mentioned in the last video, I am not instructing this course this term. I taught it back in 2019, but since then I've kind of stuck to my specialty, which is solid mechanics. But I wanted to give you guys these lecture videos to hopefully help, but it's actually good that I'm not teaching it this term, because since I'm not teaching it, I'm able to give you guys kind of the secrets in exams, and that's what I like to do. So this is where the real meat of engineering starts, is vector addition. It's going to be the first real topic that may puzzle a couple of you students, but don't worry, we're going to go through it together, and I'm going to tell you all the secrets that professors love to throw onto exams. So with that being said, let's jump into it. So, as we kind of mentioned last time, vectors are a little bit different in that they follow specific mathematical principles for multiplication, addition, subtraction, etc. Now, in the last video, we covered multiplication by scalar, and as we said, it's actually pretty simple. We just scale the vector accordingly and maybe flip the direction if the scalar is negative. Now, when it comes to addition and subtraction, it's actually a little bit harder than addition and subtraction, because as we mentioned, vectors have direction, and this direction must be accounted for. So vector addition, in essence, is going to follow the parallelogram law of addition. And you're saying, Clayton, well, what exactly does this mean? Well, let's say that we have two vectors. We have vector A and we have vector B, and we want to add those bad boys together. So what I want to do is I want to create a vector C, which is vector A plus vector B. Well, what I would do is I would take vector A, place it down, and then I would take vector B and place it on top of vector A. And the resultant vector C is going to be this green vector here. So it's going to start at the tail of A and go to the head of B. Now you guys are saying, Clayton, you're an idiot. That's not a parallelogram, that's a triangle. You're right. So why is it called the parallelogram method? Well, notice how I started with vector A and then went to B, because A, B, C, D, of course I would do it that way. But if we were to start with vector B, and place that one down first and then move on to vector A, now you can see that we actually created that parallelogram. So the key takeaway here that I want you guys to know is it does not matter which vector you start with. You can start with A, you can start with B. Don't be chained to those normal rules of 1, 2, 3, A, B, C. You can start off with whatever. It's one of the things that professors like to kind of trick students. They'll give you F1, F2, F3, etc. And naturally, as a student, you want to go F1 first, then F2, then F3. It might be a little bit more difficult, even though the answer is going to be the same. So start with the vector you guys feel most comfortable with. Now, to actually add these vectors and analyze them, we have two possible methods. The first one is the parallelogram method, which we're going to be covering in this video, and the second one is the Cartesian vector notation method, which we'll be covering in the next video. As I've already mentioned, this parallelogram method, you guys will hate it. Students hate it, and the reason why is it's trigonometry based. No engineer likes trigonometry. If you say you like trigonometry, well, you're a math student. You're not an engineering student. So this is typically why students hate it. And the Cartesian vector notation method, as we're going to see, it's much easier and it's going to be the preferred method. And that's actually a good thing, because for the remainder of this course, all the way until week 12, we're going to keep the ideas of Cartesian vector notation. So parallelogram method, it's nice to learn. It's going to be a bitch to learn. But at the end of the day, it's going to appear on maybe one assignment. And if your professor's kind of a troll, then they'll throw it on something like a midterm. But other than that, you won't see it too much. Nevertheless, we have to learn it, so let's figure out how exactly we learn it. So the parallelogram method directly involves solving that parallelogram that we created in the previous slide using trigonomic identities. The problem, however, is that if we remember that parallelogram, it wasn't a nice right triangle. We didn't have 90 degrees anywhere. So we have to go to a little bit more complex type of trigonometry, which is the sine law and the cosine law. I say complex, but you guys are very smart kids. You guys are going to say, Clayton, are you joking? This is simple. It's not complex at all. So let's review what sine law and cosine law are. So if I were to have a triangle, so again, notice that this is not a right triangle. Again, very rarely will you guys see a right triangle using the parallelogram method. And if we have this triangle, we can define each side length. So again, these are the lengths of the sides as capital A, B, and C. So again, these are the side lengths. And inside of that triangle, we have three angles. So we have lowercase a, b, and c, and we call these interior angles. Now note that I put the interior angle small a opposite from side length A. So that's kind of a little fun fact to help you remember where these angles are. Now the first law we're going to talk about is sine law. Now sine law is very great because it relates a side and an interior angle to another side length and another interior angle. So we're going to typically use this if we're solving for another interior angle. In these types of questions where you're given two vectors to add together, well, you have the two vectors. So you know what capital A and capital B are going to be, and using some trig you can find out what maybe small a is. So finding that other interior angle is actually going to be quite easy. Now that's sine law. We also have cosine law. It looks a little bit more gross, but if you look at it kind of intuitively, you'll notice a pattern. So it's not that hard to remember. Now we typically use cosine law to find side lengths. And the key giveaway here is when we look at the equations, we have the side length is equal to something. All right, the side length is equal to something. So typically what we do in these problems is we solve for our resultant force C using cosine law, and then we solve for the angle of C using sine law. And when we go through the procedure, it's going to be very apparent here. Now, if you guys are thinking, Clayton, these are a little bit complex, I don't know if I can memorize them. Well, good news for those of you at the University of Alberta, these will be on your formula sheet. All right, so these are going to be on the formula sheet. You guys won't have to memorize them. And as I'm recording this, I noticed that I don't have b squared at the bottom. So note in cosine law, we have c squared is equal to something, a squared is equal to something, and it should be b squared is equal to something. I'll update that in the notes before I hand out the notes to you guys. So that's kind of the trigonometry that we are going to use in the parallelogram method. Now, I may have given you guys the trigonometry, but the method still makes no sense. So let's do a little bit of an example procedure on how exactly we use this method. So let's say that you have a question and the professor says, I give you vectors A and vectors B. I give you an angle vector B makes with the horizon and an angle vector A makes with the horizon. And I want you to add these two together. So this is a very typical assignment or exam type question where they give you two vectors, they give you some geometry of the vectors, so an angle, and they say add them together. Well, the first step that we want to do is we want to create that triangle. Remember, we're going to utilize our trigonomic identity, so we need to create a triangle. So what we're going to do is we're going to take one of the vectors and we are going to place it on top of the other vector. Now remember what I said, it doesn't matter which one you guys do. So if you guys want, you guys can take B, place it on top of A, or you guys can take A and place it on top of B. For this particular one, I'm going to say, all right, I'm going to take A and I'm going to move it at top of B. So that's the first step, is moving one of the vectors so that the ass of the one vector is at the head of the other vector. The next thing that we're going to do is we're going to draw our resultant vector to create that triangle. So remember that the resultant vector is going to start at the tail of B and go all the way to the head of A. So in this case, our resultant vector C is going to start at the very left side and it's going to kind of go up to the right side over there. And now if we look, we have a nice triangle. Now this is where the cosine law and sine law are going to come into play because we can start solving for this triangle. So the first thing that we have to do is we have to solve for an interior angle. And you guys are saying, Clayton, well, why do we have to do this? Well, remember that in cosine law, if we're trying to solve for the magnitude of C, we need one of those interior angles. In this case, we need interior angle C, which is going to be over on this side. Remember, the magnitude of A and B is something you're given in the question, so we almost have all the pieces to use cosine law. The last thing that we need is actually going to be that interior angle C. The problem is if we look at this, it's not really apparent how we find interior angle C. And this is why the parallelogram method is a bitch, because it requires a lot of trigonometry, which again, students aren't really a fan of. So how do we find that interior angle C? Well, the best way is to use the fact that we can draw a horizontal line. If we look at this horizontal line, we know that the angle it makes of a half circle is 180 degrees. So if I know the angle on the left side of C as well as the right side, well then I can figure out what C is. So the question is, what are those angles? Well, if we look at the left side of C, we actually know that that angle is going to be alpha. This is trick number one when it comes to engineering trigonometry. If I have a line here, and this is a pencil of course, but if I have a line and I know this angle on this side, well, the angle on the other side is going to be the exact same. That's trick number one, and we're going to cover this more in our example videos, but that's the only real trick you need to know in engineering trigonometry. So now that we know the angle on the left side, we can say, all right, well, I can figure out what C is if I know the angle on the right side. Well, this one's actually even easier because we know that angle is simply going to be beta. We already given the angle vector A makes with the horizon down below, so we can just kind of copy it to the top now. So remember, alpha and beta are something that we are given initially in the question. So if we want to find interior angle C, all we need to do is go 180 degrees minus alpha minus beta. We have what our C is. Now, since we know what C is, we can actually solve for the magnitude of vector C using cosine law. We have all the pieces we need. Remember, we needed the magnitude of A, the magnitude of B, and that interior angle C. So at this point, we're good to go. We know exactly the magnitude of C. Now, here's the trick. If you guys were to just finish the assignment or exam and saying, you know what, here's your interior angles, or sorry, here's the magnitude of C, I'm good to go, the professor's just going to laugh at you and say, okay, well, that's one step of the puzzle. Another thing that we have to do is we have to give some sort of indication of the direction of C. Remember that a vector is a magnitude, which we just solved for, and a direction, but we haven't really specified a direction. If we look initially when we're given vectors A and B, they gave us the angles alpha and beta to define that direction. So we need to figure out an angle to define our resultant vector, C. How do we do this? Well, we're going to go to sine law and we are going to start solving for interior angles. Now, if I'm looking at C, one interior angle that might be useful is going to be this interior angle A. Now, this is great because we can use sine law, because remember, in sine law, if we have a length and an interior angle, we can solve for the interior angle if we know the other length. In this case, we know the magnitude of C as well as interior angle C and the magnitude of A. Therefore, we can easily solve for that interior angle A. So at this point now we have that light blue interior angle A. Well, from there we can say, all right, if I know what alpha is and I know what A is, well, I can figure out what this angle gamma is, which is the angle that C makes with the horizontal axis. So that's going to be another trick, especially for you high school students that are just coming into engineering, is when we're defining the direction of C, we always give it in terms of an angle with the horizontal axis. So in this case, I would say that C is maybe 32 degrees with the x-axis. If I were to say that C is northeast, again, that's a very high school thing, using in sort of those directions, you guys are going to get marks taken off. You guys probably won't get any marks at all because it's actually incorrect. So remember, when we're specifying the direction of these vectors, we have to give it in terms of an angle. You guys can't say north, south, east, or west. That'll make no sense. Remember that we have it in terms of an angle. So that's basically the parallelogram method. The problem is we have a couple special cases that professors like to kind of throw at you to test your knowledge. And the first one is vector subtraction. So again, we just talked about how we add two vectors together. What happens if we want to subtract them? Well, it's actually really simple because subtraction is a special case of addition, just like how division was a special case of multiplication. If I wanted to take vector A and subtract vector B to get my new resultant vector C, well, this is the exact same as going A plus -1 times vector B. Now, we covered multiplication by a scalar in the previous episode, so we already know that what -1 does is simply flip the direction of the vector. That's all it does. So if I were to take these two and add them together, all I need to do is flip vector B before doing the addition together. So if I have vector A and vector B just like this, and I want to subtract vector B from vector A, well, my methodology would be exactly the same, just with that little trick thrown in. So I would place A down, something like this, and if I were to add them together, normally I would place vector B like that, but since I'm subtracting them, what I would do is I would actually flip vector B the other way, and then I can create my resultant vector C. And then if we look here, we have our triangle again. We can solve for those interior angles, and we can solve for everything that we need. So again, it's just a special case of addition. All you guys need to do is flip the vector you're subtracting, and you're good to go. The last thing that we're going to talk about, and this is if the professor wants to be a real ass, is the addition of 3 or more vectors. We just talked about adding 2 vectors together. And adding 2 vectors, it kind of sucks because we need trigonometry, but you guys are all very smart students. You guys can handle it. The pain in the ass comes in is when we have 3 or more vectors, because we don't really create a triangle. And you're saying, Clayton, how do we not create a triangle? Well, let's take a peek. So let's say that I had 3 vectors, A, B, and C, and I want to add all 3 to get vector D. Well, using the procedure we learned before, we place A down, then we place B down, and then we place C down. Well, we can see that our resultant vector D is going to look something like this. Well, if you guys are solving it this way, all I can say is good luck, because if we look here, we didn't create a triangle. And if we didn't create a triangle, we can't use sine law or cosine law. So the angles here become a real bitch real fast. So this is not the way that we actually add 3 plus vectors together. We do something very similar, but basically we split it into steps. So if we add 3 or more vectors, all we're going to do is we're going to add 2 vectors at a time to create intermediate vectors, which are then added to the remainder vectors. You're saying, Clayton, that sounds a little crazy. What do you mean? Well, if I was to solve the situation above, I would place A down, and then I'd place B down. Now, at this point, I have my 2 vectors down, so I'm going to solve for an intermediate vector, which I'm going to call R1, which is A plus B. After that, I'm going to take that intermediate vector, and I'm going to add the remainder vectors. So in this case, I've already added A and B together, but I still have C left. So I'm going to place C now on top of R1, and then this will give me my resultant vector D. So it's just a matter of splitting it into steps, and from here I can solve for our resultant vector D. And that's it. That is vector addition using the parallelogram method. Now, another thing that I'm going to probably mention at the end of every one of these videos is the best way to really understand this is through examples. The best way to understand the theory in this course is through actual applications. So if you guys look in the description below, I'm going to have 2 example videos, one on how to add 2 vectors together, and then one, of course, to add 3 vectors together, just to kind of cover everything we learned in this video here. I like to keep the theory short and sweet, and then really discuss all the tricks and stuff in the actual example videos, because even though professors deny it, I believe that this is truly the best way to learn this course. It's just through solving examples. So yeah, that's it for this video, guys. Thank you guys so much for listening. I will see you guys in the next video.